Hi everyone, again welcome to the course of structural biology. We are continuing with the structural biology techniques, and again in structural biology technique we are talking about X-ray crystallography. Today is the last class of the module, and in this class we are going to discuss data collection and processing. But before that I would talk about the journey so far. So, the journey of X-ray crystallography technique, what we did, what we learned. So, if you remember, we start with targeting the gene, because proper targeting is very important. After targeting, we optimize the gene with engineering, then we find a host system, vector system, and that help us to go for cloning. Once the gene is cloned, we go for overexpression, because overexpression is very critical here. We do overexpression, then we need to go for purification. We have discussed that, and then for protein we have to do double check. One, ultra purification, second, folding, because if the protein is not folded you are not going to get a crystal. So, this is the process which is common to most of the structural technology. We are going to discuss after that. Now, when we have protein we go for crystallization. As discussed, crystallization is a process which is the check line. Like if you do everything perfectly, still you have a problem, it is the crystallization, and we have spent a lot of time looking at how to crystallize, what are the factors affecting crystallization, though we also admitted that there is it's even not considered as a science, it considered as arts, like we do the process, it is rather the maintaining of the process and depending on luck. So, but we did whatever. So, we also look at the science, what the phase transition is happening on, how the phase transition could be affected, how our process could work on that and all. And also we discuss some modern method by which you could improve, and among them one very important is using microfluidics in ISMA Globe Lab in Chicago. And then from crystallization we got crystal. So, we looked at the crystal, we check the crystal is protein crystal or not and all, we go for diffraction. Here we stopped kind of, we looked at unit cell, lattice, symmetry, as well as instrumentation. So, this is our journey so far, and in this technique today we will look at the diffraction pattern, how it is coming. So, today we will see that how the image happens to be a 360-degree rotation in phi collected on a CCD detector with all goniometer angles set to 0, which we talked about how we could change the angles, so make it fixed, make it aligned, because alignment is very critical. If you don't align it, then with the rotation the crystal will lose the main contact of the beam and you would not get data. So, we did the alignment, and if you look at the X-ray diffraction pattern from a single crystal which is a protein crystal, you will get a set of spots and we will look at their relation. So, before going to that, we will take a look how the thing is happening, what are the science behind it. So, it is very analogous with light, and if you look at interaction of light, it interact with a matter and then several things happen. It could reflect, it could transmit, it could absorb, it could scatter. Similarly, here in X-ray we will look at how its interaction affecting matter. So, D is the space, and there are several phenomena like incoherent scattering, which is also known as Compton scattering, coherent scattering, which is Bragg scattering, which we are interested, absorption, which follow Lambert-Beer's law, fluorescence, photoelectrons, and of all the effect produced by the passage of X-rays through matter, we are primarily interested in the coherent scattering, as I told, that maintains Bragg's law. These are the X-rays that we measure in diffraction experiment, as the scattered X-ray carry information about electron distribution in materials. So, let us look at coherent scattering. The ray comes and hit the electron, and electron goes in different directions. So, incoming X-rays are electromagnetic waves that exert a force on the atomic electrons, and that is why you get the molecular imprint. You hit a carbon, you hit a nitrogen, you hit a oxygen, you see different effects, and based on that effect, what is coming and detecting, we could go back and calculate which atom it is. We could make the model, we will see that. The electrons will begin to oscillate at the same frequency and emit radiation in all direction. So, in coherent scattering, there are constructive and destructive interference, which is, you all know, the property of any wave when they are like having in the same same phase, they are constructive. When they are in opposite phase, they are destructive. So, coherent scattering by an atom is the sum of the scattering by all of the electrons. Electrons are at different position in space. So, coherent scattering from each generally has different phase relationship. At higher scattering phase, and if I do not miss, this phase would be very important for us for further discussion when we are going to solve the equation, when we will go to get the electron density, we will see that. At higher scattering angles, the sum of the coherent scattering is less. So, coming to diffraction, because among the coherence, it is the diffraction which is important for us. A diffracted beam may be defined as a beam composed of a large number of scattered rays mutually reinforcing each other. If you see, this is scattering when the X-ray come and hit a particle and go into different direction, whereas when it hit a crystal, its interaction with the crystal is called diffraction. That is the difference. So, random arrangement of atom in space give rise to scattering in all direction, which have weak effect and which also affect the intensity. But when atoms are arranged periodically in space, which is a crystal, in a few specific direction which satisfy Bragg's law, there are strong intensities in the scatter beam, that is called diffraction. That is what we are looking at, that is where we call the data collection. No scattering along direction not satisfying Bragg's law. So, if you remember, we will talk about Bragg's law and how there is a deviation of original Bragg's law, we will discuss. But before going into data collection, let us look at the history, let us look at where it starts. It starts at 1912 when von Lau is performed, they performed their own experiment, if you remember, with copper sulphate. In 1913, Bragg started. They are father and son, as we talked about. They worked for a long time. They developed diffractometer, they developed detector. They could be considered as the father of X-ray crystallography. In that way, contributed a lot. In 1965, there was improved film, mostly contributed through Weisenberg, but there are many other contributors as well. 1960 to 1995, it's serial detector diffractometer. Okay, so they have to collect one by one. So the amount of data set collected is really less because it takes a long time to collect. As the statistics told, it is 50 data set a year. Think about, you could only have 50 crystals solved. So if you go back to the protein data bank, I will talk about that in detail. Protein data bank is a database where all the experimentally solved structures are deposited, the coordinates. If you see, you will clearly see the trend. What I am talking about, data collection have influenced greatly how the data was submitted there. After 95, image plate came, CCD detectors arrived, and it reduced the data collection to a few hours of collection time for a routine structure. Then after 2007, there are digital detectors which are currently using Axiom, Pilatus and all, and there are new options coming up. You know, when we think about data collection, we always talk about the opening and closing of shutter, but now there are shutterless option is coming, the noise is reduced, the intensity is enhancing. So with crystals, which we have never thought data could be collected enough to solve a structure, now that data, like that crystals, are also being able to be solved, and we are getting structure out of that, specially called about twinning. Twin data, which were like when I started crystallography, protein crystallography, we used to get twin data, like twin crystal. We generally throw the crystal and try to get new crystals. Sometime we solve, but now they are solving regularly. So these are the improvement. Coming to data collection, the source of X-rays is often home source of synchrotron, which I talked about. For our consideration for further processing, let us assuming that we are collecting data in a home source. The typical size of a crystal for data collection may be 0.3 into 0.3 into 0.1 to 0.5, 0.5, 0.1 millimeter. That is big crystal. If you have smaller crystals, as I talked earlier, you don't like to collect data in home source, or even if you collect, you don't get the actual resolution you want to solve in the molecular level, atomic level. So you need bigger crystals. But again, with the improvement of instrumentation, we are actually getting diffraction patterns of smaller crystals in home source also. Generally, a crystal is mounted on the phi axis of spindle, which lifts the crystal upside down or reverse, upside down or up depending on the setup of the instrument. The crystal can either be mounted in a capillary tube or for room temperature data collection, or more typically in a mounted cryoloop. I mostly discussed about mounted cryoloop because mounted cryoloop is the general way to collect data, like more than 90% data we collect with cryoloop, but there are also capillary process which I talked little bit. So you have a capillary, you put the two side close and you have the crystal and you put the mother liquor. So what is the disadvantage? There are many disadvantages. What is the advantage? Let us talk about the advantage. Is when you want to collect the data at room temperature, when you cannot take temperature of minus 180 degree with nitrogen gas or liquid nitrogen, you cannot do freezing. That time you try with this capillary tubes. After the crystal is mounted on the instrument, the video screen I talked about in the home source, there is a video screen is used to align the crystal to the presumed center position of the X-ray beam. And I also explained to you like before that how this alignment is very essential, because you set it and then it would automatically rotate, it would automatically rotate. So, if you do not do the perfect alignment with rotation, it would lose the main center, like it would lose the focus of the X-ray beam. After alignment, the detector distance is set. You have to set the detector distance, the phi axis is locked and enclosure doors are closed, and the shutter switch, as I told, the shutter switch is moved to the external position. So, we generally had to do that. Now, newer instrument is coming where it is going shutterless. The crystal is then ready to collect a few initial oscillation images, one at 0 degree and second at 90 degree. I did not talk about these. So, what happened when we start data collection, we do not just go and do the data collection. If you remember, generally it takes 2-3 days. So, before you spend 2-3 days and that much of X-ray power consumption and all, you have to make sure that the crystal you are diffracting is going to give you a good data. So, how you ensure that? We collect 0 degree, 90 degree, and that also help us how much exposure time you give. Think about if you want to collect 360 degree images. So, 360 per degree, 360 images. Okay. So, if you choose 1 minute, that is 6 hours. If you choose 10 minutes, that is 60 hours. So, there is a difference of 6 hours to 60 hours just if you change the exposure time to 1 minute to 10 minutes. That is why it is very critical to initially do as much as optimization. So, we collect one at 0 degree and a second at 90 degree. Okay. During collection of the oscillation image, the crystal is rotated about the phi axis for about 1 degree. This is also depend on you. You could make it 1 degree, 0.5 degree, 0.25 degree. It is depending on you. As the crystal is exposed, as average 2 to 5 minutes per image we do, but that also depends on how your crystal is diffracting. So, this part you need actually expertise. Okay. You collect a few, I talked about 0 degrees and 90 degrees, but you collect few, and then what you have to do is called indexing. I am coming there. The initial images are inspected for crystal quality and the software then automatically indexes the crystal. So, this indexing, definitely you could look at by eye your diffraction, but indexing is very important. Further, the collected data would be combined computationally with complementary chemical information to produce and refine a model of the arrangement of atoms within the crystal. That is the further process, and final refined model of the atomic arrangement, now called a crystal structure, is usually stored in public database. After the diffraction pattern is obtained, the data is then processed by a computer and the structure of the atom or molecule is deduced and visualized. So, these are further process. Let us concentrate on indexing now, because as a new crystallographer, indexing is very critical for you. So, here we have to talk or think about two separate things. Two separate pieces of information can be found in the reflection of the diffraction image. The first comes from the geometrical arrangement of the reflection, which gives all the information about the crystal lattice and the symmetry of the crystal. And now you start realizing why I have spent 2 classes to explain you about the crystal lattice, about the unit cell, about the symmetries. They are important because they will now help you to understand the indexing. The second comes from the intensity of the reflection that gives part of the information about the content of the lattice. So, first choice of unit cell, and it's critical. Why? Let's take an example. Suppose you have your pattern like this. Okay. Now, I choose this. So, I most probably it look like choose a cubic type of crystal. You choose something which is kind of in a different space, which is like and both are possible. So, whatever your crystal is, whatever experiment you are doing, even if A and B both are doing identical experiment, they could come up with different unit cells. Choice of unit cell is depending on your choice of model. But then there is a trick. Remember I told, suppose I chose unit cell A and you choose unit cell B. You get lower symmetry and I got higher. Then I have to do less work than you. So, that is why there is also needed to be a thing which is called optimization of choosing unit cell. That is important. The second comes from the intensity of the representation. Yes, unfortunately, the second kind, which is the one that we are actually interested in. So, this is what indexing is. The second one, which we will discuss later in the next module. Here we have a thing that we lack phase. So, first we are doing the indexing, means we are finding the unit cell, then we are going to get the actual coordinate, actual intensity, the electron density. For that we lack phases, which is called the famous phase problem. We will talk in details about that, what is the phase problem and how in protein crystallography people have solved phase problem. So, indexing and further data collection. The indexing procedure determine the unit cell dimensions and lattice type of the crystals, unit cell dimensions and lattice type of the crystal, as well as its orientation relative to the X-ray beam. We could use software like HKL, MOSFLM, there are many others. After indexing, the software determine the base starting and ending rotation angle for the data collection. So, this is extremely critical. These, so three things are important. Here the initial images would be utilized. First, how much exposure you are going to give, and then what would be your starting and ending rotation angle. So, rotation angle range, and third, what would be the degree of interval. Are you going to give 1 degree, 0.5 degree, 0.25 degree. These three things are practically very critical for getting good data in less time. Think about, I already talked about exposure, you put 1 minute and 10 minute, there is like around 10 times, you could easily see this is proportional. Then the rotation angle, if you put 90 degree or 180 degree or 360-degree, there would be 4x difference. Then the rotation, you make 1, you make 0.5, you make 0.25, again the difference is 4x. So, actually there would be a 10x into 4x into 4x. So, 160x time difference, depending on how good you have optimized. And then you set up the time of image collection, number of oscillation image to be collected, which take you overnight. Even if minimum, it takes 24 hours or something like that. During indexing, the spots have to be found, named with integer number, and the crystal geometry has to be determined accurately. This results the intensities to be integrate. So, you need integration, integrate accurately, that the space that has to be modeled later on is defined accurately. So, if you look at this is the diffraction pattern we have shown before, and remember I talked about there are, like, for getting a good diffraction, your crystal ordering would be perfect. There might be rotational disorder, there might be translational disorder. If that is not, you get the points, and you see the numbers I have put. What is the number? These numbers are HKL, which is Miller indices. Development of Miller indices is another step towards success in protein crystallography. We will discuss about that in details. So, relation of the lattice and the spots, the length of the reciprocal lattice, see this is now arriving. Reciprocal lattice and Miller indices are related, we are going to talk about that. The length of the reciprocal lattice vector is of the order 1a. If a is the base vector, this is 1 by a. Small lattice, like in elemental solids, big reciprocal lattice points well separated. For example, if a lot of small molecule synthetic chemists work, like solve their structure of their small molecule through X-ray crystallography, for them that is not a problem, but it is a problem for protein which form big lattices. The spots, like bigger the lattice, smaller the spot, because this is inversely proportional. So, for the protein crystals, there are big lattices, so the spots are closer. And so, now because it is closer, it should not be mixed up. So, it should be, the beam should be very collimated monochromatic beam. And now you remember, if I talked about yesterday about the previous class about the collimated monochromatic beams. We already talked about sources, but just to remind you, a highly collimated and monochromatic beam is needed for protein crystallography, and for that it is only be provided by synchrotron radiation source, and when you do not have synchrotron radiation, you have good X-ray home source. Now, going towards the further analysis of the data, we will come to Bragg's law, which is n lambda equal to 2d sin theta, where n is a integer, and you see that law is applied for the parallel planes where the light ray or any X-ray is coming and diffracting. N is the order of reflection, d is the plane of spacing, and theta is the Bragg angle. Now, we will talk about this plane spacing as a by root over h square plus k square plus l square, where a is the base vector which we talked about, the ABC, and HKL is the reciprocal lattice. Path difference must be integral multiplies of the wavelength theta in equal to theta out. So, coming to the geometry of the Bragg's law, the incident beam, the normal to the reflection plane and the diffracted beam are always coplanar. They have to maintain same plane. The angle between the diffracted beam and the transmitted beam is always 2 theta. Sin theta cannot be more than unity. So, it require n lambda less than 2d, for n equal to 1 lambda less than 2d. So, lambda, the wavelength should be less than twice the spacing we want to study. So, this is a condition, which will help you to choose your matter which you are using, the metal you are using here. So, we are using copper with K alpha 1.54. So, we are rewriting Bragg's law as lambda equal to 2 sin theta into d by n. D is the spacing and n is the periodicity. A reflection of any order as a first order reflection from planes, real or fictitious, spaced at a distance 1 by n of the previous spacing. If we consider that as a d prime, that is equal to d by n. So, lambda equal to 2 d prime sin theta. An nth order reflection from HKL planes of spacing d may be considered as a first order reflection from the NH, NK, NL plane of the spacing d prime equal to d by n. So, that satisfies, and here throughout we are talking about reflection is only because when we are talking about symmetry, we talk reflection between the incoming and outgoing beam. Otherwise, we will talk about diffraction. So, coming to what I was talking about, reciprocal lattice vectors used to describe Fourier analysis of electron concentration of the diffracted pattern. We will talk about the Fourier analysis later. Every crystal has associated with it a crystal lattice and a reciprocal lattice. A diffraction pattern of a crystal is the map of reciprocal lattice of the crystal. So, what is reciprocal lattice? If you think about the planes, they are going parallel. So, when you are getting the ABC, sometime it would be infinity and all, so it is a problem. The reciprocal is 1 by, so when it is infinity, 1 by infinity is 0. In that way, reciprocal lattice is helpful. So, what is reciprocal space? The immediate result of the X-ray diffraction experiment is a list of X-ray reflection HKL and their intensities I. We can arrange the reflection on a 3D grid based on their H and K and L values. The smallest repeat unit of this reciprocal lattice is known as the reciprocal unit cell. The lengths of the edges of this cell are inversely related to the dimension of the real space unit cell. So, in previous classes I talked about real unit cell, real value of the space. Now, a reciprocal is just inversely proportional, and that is what making the calculation much easier and probable. This concept is known as reciprocal space. It emphasizes the inverse relationship between the diffracted intensities and real space, and you will understand even more when we will go to evil space. So, real space and reciprocal space, you have a crystal structure, it is having crystal lattice, it have unit cell document. When it comes to the diffraction pattern, you get a reciprocal lattice, and that help you to get the structure factor for further solution. So, this is the real space lattice, and this is the reciprocal lattice. So, in real space what information you get? You get the unit cell A, B, C, alpha, beta, gamma, the base vector, their value and their angles, electron density, the rho, because I will show you how to perform the Fourier and how we come to electron density. Atomic coordinates, thermal parameters which is B factor, we will talk about that, bond length, bond angle, bond length would be in angstrom, bond angle would be in degrees, and the phases of the crystal which we also discussed. In the reciprocal space we get the diffraction pattern, we get the reflections, we get integrated intensities which is HKL is the reciprocal space like in I is the intensity, and structure factor which is FHKL, phase which is alpha HKL. So, if you see these planes must intersect the cell edge rationally, that is the reason we are talking about. Otherwise, the diffraction from the different unit cell would interfere destructively, that is the condition. We can index them by number of times HKL that they cut each edge. The same H, K and L values are used to index the X-ray reflection from the plane. So, if you see here it is 3 minus 1 and 2, or with the inverse operation minus 3, 1 and minus 2. So, examples of diffracting plane and their Miller indices. It is a method of identifying diffracting plane in the crystal system. A plane is identified by indices HKL, they are called as Miller indices, that are the reciprocals of the fractional intercepts that the plane makes with the crystallographic axis or the real axis. So, they are inversely proportional. So, you have A, B and C, and if you see in case of Miller indices, you actually get all those in integer number 001, 100, 010, 101, 110, 011, 111, 1 bar 1, bar 1, 11. So, they are all integers, that is the biggest advantage. Here you get integer or 0, whereas you get for real axis you get fraction or infinity. So, diffraction pattern which we are talking about, the two successive CCD detector images with a crystal rotation of 1 degree per image. For each X-ray reflection, which is the black dots, you would see indices H, K, L can be assigned and an intensity I equal to F square is measured. When Bragg's law is satisfied through the appropriate combination of crystal orientation angles with respect to the incident X-ray beam, reflection appeared on the detector. Previous example which we talked about shows two successive CCD detector images with a crystal rotation of 1 degree. A complete data set consists of the measurement of all independent intensities in the diffraction pattern out to a specified resolution limit, which means if you have to collect 90 or 180 or 360 or 720 images, each of them have one intensity, and then you have independent intensities, 90 independent intensities, and you get the summation of that to get the total number. Coming to the concept of Miller index. A Miller indices form a notation system in crystallography for planes in Bragg lattices. We know about Bragg lattices. Characteristics: they are set of 3 integers H, K and L, inversely proportional to where phase or crystallographic plane intercept axis. So, there are intercepts, that is what important. A crystal lattice may be regarded as made up of an infinite set of parallel equidistant planes passing through the lattice points, which are known as lattice plane. If you remember, when we made our journey from 1D to 2D to 3D, if you consider the 1D lattices, it is equidistance. So, these have this here, but these also have this here, and these have this. So, this will have this. So, in that way they will go in both the direction. So, they will create infinity. Here in Miller index, the crystal lattice may be regarded as made up of an infinite set of parallel equidistant plane passing through the lattice point. So, now in simple terms, the planes passing through lattice points are called lattice planes. For a given lattice, the lattice planes can be chosen in a different number of ways. So, as you see here, these are Miller indices of different lattice space where all the points have same spacing, which is d, but you have to get the relations where they intercept from the parallel lines. The orientation of planes or faces in a crystal can be described in terms of their intercepts where they are cutting on the 3 axes. Miller introduced this system to designate a plane in a crystal. He introduced a set of 3 numbers which we call HKL Miller indices to specify a plane in the crystal. This set of 3 number is known as Miller indices of the concerned plane. So, Miller indices is defined as the reciprocal of the intercept made by the plane of the 3 axes. Let us see how you could get or find a Miller indices. Determine the intercept of the plane along the axis xy. So, if you have this, so xy, y, z in that way in terms of the lattice constants a, b and c. Determine the reciprocal of these numbers, find the least common denominator and multiply each by this least common denominator. So, get the integer. The result is written in parenthesis. This is called Miller indices of the plane in the form HKL. So, if you see here, you get the planes, and this is 1 2 3, this is 1 2 and this is 1 2. So, in x axis around this is 2 units, 3 units along y axis and 2 units along z axis. If you see 1 2, 1 2 3, 1 2. So, in that way you could determine. See, look at this, these have 1 2 3, 1 2 1 2, right. The intercepts are 2 3 2 on the 3 axis. The reciprocals are then, so it is 1 by 3, it is 1 by 2 and this is 1 by 2. So, the intercepts are 2 3 and 2 on the 3 axis. The reciprocals are 1 by 2, 1 by 3 and 1 by 2. The least common denominator is 6 multiplying each reciprocal by LCD, least common denominator. So, we get 3 2 and 3. Hence, Miller indices of the plane is 3 2 3. So, you get the intercepts, you get 2 on the x axis, you get 3 on the y axis and you get 2 on the z axis. So, you will get 1 by 2, 1 by 3 and 1 by 2. Now, you have to make them integer. So, you multiply into 6. So, you get 3 2 3, that is the Miller indices. So, coming to the X-ray diffraction data processing, which we are going to discuss in the next module. From data collection, we have found number of the oscillation images. In data processing, a set of oscillation images is converted into a file that contains the intensities I and the sigma of all of the symmetrically unique H-scale reflection that were measured. There were essentially 4 steps involved in data processing. collection of initial images, crystal evaluation and indexing, which we talked about. We will talk about that also, the optimization next class, next module. Collection of full set of oscillation images, integration of reflection intensities and scaling, merging and averaging of reflection intensity data. We talked about what is unique HKL reflection. We will talk about what is intensity and sigma. So, and then we will proceed with the solution. Thank you very much for listening to me. Send the questions. Please continue listening. Please continue learning. I will try my best to come up with much better things in the following classes. Thank you very much.